This is our intro video for AP Calculus BC, section 3.8, Newton's method. Just so you know, Newton's method is not on the official curriculum framework for the AP Calculus, but still an interesting topic nonetheless. And I just wanted to share this with you. So Newton's method is a method for using a tangent line to approximate the real zeros of a function. Pretty amazing fact that over the years, over the decades and centuries, it has been proven that you can find a general method for finding the zeros of a first degree, which is a line, second degree, which is a quadratic, third degree, and fourth degree. But the thing that's amazing is that it has been proven that you cannot find a way to find a general solution for a fifth degree or above polynomial. And so kind of an amazing thing to say that you know for sure that it has been proven that you can't find an answer, or you can't find a method to find an answer for a particular question. So in those cases, Newton's method is definitely the way to go, or one of the ways to go. And so this is going to be based on the tangent line, and so I thought we would review just a little bit the tangent line. I've got this blue curve right here, you can all see that, and then a red tangent line. This point that I'm going to try to draw in right here, that's called, it's in green right there, I hope you can see that. That's called the point of tangency. So there's a couple of things right here that are pretty important for us to remember. At the point of tangency, the x, y for the curve and the x, y for the line, are exactly the same. So the xy for the curve and the xy for the line are the same. So in other words, the value of the coordinates of the point are the same. And then also at that point of tangency, the slope of the curve is equal to the slope of the line. That's only true, of course, at the point of tangency. Those two things are true. Any other point along the line or the curve, those two things would not be true. But at that point of tangency, that is true. So it's a pretty important thing for us to think about. Okay, so the formula we're going to use for Newton's method comes from the equation for the tangent line with that point of tangency. Looks like I need one more parenthesis in there. There we go. With the point of tangency, x1 comma f of x1. So that would look like this. Y minus the y coordinate is equal to slope times x minus an x coordinate. So that would just be the equation of the tangent line in point slope form. And so what we're going to do with this, we're going to be trying to find the x-intercept, or the zero of this tangent line. So in order to do that, we are going to plug a 0 in for y, so that when we plug a 0 in for y, we get 0 minus f of x equals f prime of x times x minus x1. And from that, we can continue on to derive the formula that we're going to use. So if we're going to be using the x-intercept for the tangent line, we want to understand the connection between that and the curve. The idea here is that the 0 of that tangent line will be sort of close, at least, to the 0 of the curve. And so finding the 0 of the tangent line should give a pretty good approximation for the 0 of the curve. And we'll talk about how we can make it more and more accurate. So here's the formula. Here's what we're actually going to do. We're going to take that point slope form of the line, and we're going to plug a 0 in for y, signifying that we're at an x-intercept. And I'm going to solve for x. I'm going to solve for this x right here. So the first thing I would do is divide both sides by f prime. So that would give me negative f of x over f prime of x is equal to x minus x1. And then finally, I would add the x1 over, giving me x1 minus f prime of x over, let's just make that f of x over f prime of x is equal to x. And I'm going to put a little subscript under that x. I'm going to now call that x2. So this is going to be our basic formula for Newton's method for finding zeros. And we'll use that repeatedly because Newton's method is what we call iterative. What that means is that we can improve the level of our approximation, the accuracy level of our approximation, by repeatedly doing Newton's method. So the idea would be this, like if we look at this graph down here, our first line is that red line, our first tangent line is that red line. And so if we calculate the zero, we can obviously see that the zero of the red line is clearly not the same as the zero of the blue curve. But if I were to use that approximation that I just got and improve upon it, I could maybe make my tangent line a little bit, it's a little too much, make my tangent line a little bit steeper and steeper yet. Eventually I'd be getting to a place where my tangent line is getting closer and closer and closer to the same zero as the curve. And eventually, actually pretty quickly, we're going to see that the zero of our approximation gets very, very close to the zero of the actual curve. In other words, we'll stop seeing much variation on the different cycles that we complete. So we're going to do one of these examples here together in this video, so feel free to kind of follow along, pause the video once you get the hang of this, see if you can do a little bit of it yourself, and we'll practice another one when I see you in class. Let's take a look at this first example. So this clearly says use Newton's method, so we're going to use Newton's method. I'm going to write that down again. The formula for Newton's method is x2 equals x1 minus f of x over f prime of x. Okay, so we've got this this function. Of course, it's g of x. Well, I'll tell you what. Let's make this right. Let's make these g of x's. So g of x over g prime. So you can see that we're going to be using g of x and g prime several times. It says use 3 iterations. So I've got g of x sitting right there. So I think what I'm going to do is I'm going to write down what g prime is, just so I can use this as I work through Newton's method. So g prime of x is equal to 5x to the 4th plus 1. And the question really becomes, what do we start with as far as what would be a good starting value? So what I'm going to propose is that we use the IVT to help us. Of course, we know that a zero of a continuous graph will happen wherever the value of the function, the y value of the function, changes signs. So I'm going to start off with something super easy. I'm going to say, I'll erase this here in a second, but I'm going to say g of 0. Like, what if x is 0? What do we get? So if x is 0, I get 0 plus 0 minus 1, which is negative 1. And if I try g of 1, I get 1 plus 1, which is 2, minus 1 is 1. So that tells me right there that I've got a 0 somewhere between negative 1 and 1. So, what might be a good number to guess? You could guess right in the middle. Obviously 0 being right in the middle, or excuse me, 0.5 right in the middle. Wouldn't be a bad way to go. I think I'll start there. Let's start off with a guess of 0.5, knowing that we are going to be having a 0 somewhere in between 0 and 1. So let's check this out. I'm going to erase this stuff here, and I'm going to... All right, so what I'm going to do here is say x2 is equal to x1. So x1 being my guess, I'm going to put 0.5 minus g of 0.5 over g prime of 0.5. So it's going to require a little bit of work on the calculator. I will do that. You can do that as well, and we'll kind of check, make sure we're doing okay as we work across these iterations of Newton's method. Okay, so as I ran that through the calculator, I got this. I'm going to write the whole thing down. 0.8571428,571. And I would definitely advocate that you store a value like that in your calculator, knowing we're going to use it again here in just a moment. So what I did is I stored that as A. I'll kind of use that same notation here as we do our other 2 iterations. Okay, so this right here, this is an approximation for the zeros of our curve, or the 0 of our curve, I should say. And we'll see how much better this gets. So let's try out another iteration. So I'm going to say x2, I guess if you wanted to move that up a little, one spot if you want, that's fine. So x3 would equal a, the previous a that we found, minus g of a over g prime of a. So we're just going to use that previous approximation for our x-intercept in a new cycle of Newton's method. So again, I'm going to run the calculations with this and see what we come up with. You can do the same. All right, so this time I got 0.7706821,947. I'm going to store that as B. And we're going to do one more iteration to find our, at least our third iteration will be our most accurate approximation yet. So that would look like this. X4 equals B minus G of B over G prime of B, and I'll use my calculator to figure out what that is. Okay, so this time I got 0.7552829,531. You can see that the difference between our third attempt and our second attempt certainly decreased quite a bit. If we did a fourth or a fifth or a sixth iteration, I think we would see that those differences get smaller pretty quick. So I'm going to take a second and use my calculator to find out what that zero actually is, and we can kind of compare. Maybe you've already done that. We'll see how it works out here in a second. Okay, so according to my calculator, g of x equals 0 at x equals 0.75487767. So you can see that we are accurate to the hundredths place at this point, and quite close to the thousandths place. If we did a few more iterations, we'd see that it would get even better. And so this would be our answer based on where we started on this particular example. We'll do one more of these when I see you in class next time, but I hope you have the basic idea at this point.